Buen día, ya vamos a dar inicio al… Les pido que tomen asiento, por favor. Buenos días a todos, directivos de instituciones aquí presentes. Es para mí un gran gusto poder dar inicio a la parte científica del evento. Y ahora empezaremos con la primera plenaria del Centenario de Autonomía UASLP. Para mí ha sido una locura ver cómo tantos matemáticos tienen que trabajar para hacer este evento, y también es muy impresionante también ver a los administrativos que han puesto horas extras de su tiempo para lograr este evento, horas no pagadas. Entonces le quisiera dar un agradecimiento personal a Iris Maldonado, Cristina Cázares y Luis Ángel Ramírez. Nuestra primer plenaria es Bryna, profesora de matemáticas de la Universidad de Northwestern. Bryna también es la presidenta de la American Mathematical Society. Ella es miembro de la Academia Nacional de Ciencias de Estados Unidos y ha recibido múltiples premios. Sus áreas de trabajo son dinámica simbólica, teoría ergódica y combinatoria aditiva. Ella ha hecho contribuciones en el estudio abstracto y aplicaciones de nilsistemas, como también automorfismos de grupos de sistemas Shift. Además es una distinguida jugadora de ping pong. Por favor, démosles una cálida bienvenida a Bryna.
Muchas gracias. But ping pong is not my strength. So, I am a dynamicist. I will explain to you what it means that I work in dynamics. And I apologize, I will speak in English for students who might have some trouble with it, but I can't talk about math in Spanish. So, I work in this field of dynamical systems, but much of the work that I do is inspired by Erdős. Erdős was a very famous mathematician because he had collaborators all over the world, and he was famous for posing problems, just walking up to people and saying, here's a problem and another problem, and he published lists of problems. To give you, go back please, to give you an idea how famous Erdős is, well, this is his information from the database on mathematics. He published over almost 1,500 papers. This is unheard of today. Nobody publishes that many. But his co-authors, which are on the next page, he had over 500 co-authors. Okay, so there's a lot. Okay, let's go to the next page. So there's a famous thing called an Erdős number, which is who you collaborate with, who collaborated with Erdős. And so this is my Erdős number. I have 2, meaning I collaborated with somebody who worked directly with Erdős. And you'll be not surprised that most mathematicians have very small Erdős numbers. Okay, this is a list of all the fields that Erdős worked in. You can see there are many. I want to highlight 2 of them. One of them is combinatorics. If you go to the next, it'll highlight. And the other one is number theory. Combinatorics is about counting things, and number theory is about understanding numbers, like 1, 2, 3, and the prime numbers especially. So the problems I'm going to talk about are related to these things, combinatorics and number theory. Okay, let's go to the next slide. So this is a picture just of the first 100 numbers. And one of the basic questions you can ask is what kind of patterns are there in the numbers? So for example, what do I mean by a pattern? Well, if we forward, there's the number 24. I could add 10 to it and get 34 and then 44. This is a very simple pattern called an arithmetic progression, where I start with one number, it was 24, and I add 10 each time. Another arithmetic progression here is in blue. You start with 56, and you add 11. 56 plus 11 is 67. Unless I've made mistakes, it should be adding 11 each time. So these are very simple patterns, and it's not very interesting if I tell you the numbers have these patterns in them because I put all the numbers there. So this is not very hard. But what if I take the numbers and I color some of them randomly blue and some of them randomly red? Maybe half of them about blue and half of them red, or maybe most of them are blue and a few of them are red. But I use two colors and I color all the numbers. Then I could say, okay, are there patterns in one color? So this is a different question. So this is an arithmetic progression now of length 3, 14, 15, 16. I'm adding one each time, and it turns out that all three of them were colored red. And you could ask, are there things like this always there? So for example, there's another one. Here in green, I have another arithmetic progression that happens to all be in blue, 58, 68, 78, 88. Okay, so the question is now, if I take this and I color in any possible way, do you always see one of these arithmetic progressions of arbitrary length in there? And it turns out that this is a very old theorem due to van der Waerden that was proved in the 1920s. And so what the theorem says is, however you color the integers, all of the integers, 1, 2, 3, you color all of them using finitely many colors. Maybe it's blue and red, but maybe I use 10 colors. The important point being that it's finitely many. Then it turns out that one of the colors always has an arithmetic progression of however long you want it to be. Okay? If you're looking for an arithmetic progression of length 100, there is one. It's either in red or it's in blue. You don't know which, but it's in one of them at least. Maybe in both. Okay? So this would be very easy to check if you colored most of the integers blue, like 90% of them blue. You'd look for the arithmetic progression in the blue. But it turns out it's general. And so this is a general statement about what kind of problems that are called partition regularity problems. And this is one of the first examples. In fact, there was an earlier example, which is that if you take any finite coloring of the integers, it turns out you can always find 3 integers in the same color such that the sum of the first 2 is equal to the third, meaning A plus B is equal to C. One of the simplest relations. But the important point here is that they're all A, B, and C are the same color. And this was one of the results that inspired van der Waerden to think about these arithmetic progressions. So this theorem of Schur will come back and play a big role in what I'm going to talk about later, and it's a very old one. So the second one we have here is van der Waerden, which we talked about. Any finite coloring of the integers contains arbitrarily long arithmetic progressions. And the third one is Hindman's theorem, which is a little bit more complicated. Because what we've been talking about so far, the first 2 examples, are finite patterns. You're looking for A plus B equals to C. That's a triple, A, B, C. Or you're looking for an arithmetic progression that's some number A plus B, A plus 2B, up to A plus KB, to be an arithmetic progression of length K plus 1. What Hindman did is he said you can find infinitely many integers, A1, A2, A3, and you can add all of them, and all of the integers and all of their finite sums are the same color, meaning not just A1, A2, and A1 plus A2, but also A3 and A1 plus A2, A1 plus A3, A2 plus A3, and A1 plus A2 plus A3. And it goes on infinitely often. So I won't keep repeating that because, okay, it's not going to be understandable. We'll spend the whole time listing an infinite one. And since then, there's been a huge amount of research finding many patterns. But I told you at the beginning, I am a dynamicist. What is dynamical systems? It's a way of studying things that change with time. These questions that I'm looking at are static. Okay? Wait, let's go back one for a moment. They're static, meaning they don't move. They're about find a configuration. Look in here and find some pattern. That's not a very motion question, which is dynamical systems about time and evolution and change. So let's go back to the list of topics that Erdős worked in. If you look, you will not find one subject here. And what is that subject that's missing? Dynamics, my subject, right? So if you move forward. So missing, move forward, is dynamical systems. There are no papers of Erdős that he wrote that were in the subject of dynamical systems. And yet he had a huge influence over dynamical systems, because each of these problems, it turns out, translates to something about an evolution of a system, how systems change. So I'm going to give you a very general definition of a dynamical system, and then we'll give a more specific one for our purposes later. But a dynamical system, well, we live in a dynamical system. There's a space, okay? The space might be where we live. There are points in the space. The points in the space we'll call the space X, and we'll use little x to refer to points in the space. So if the space is the world, then points would be locations, for example. Okay, then, and I could use anything. You know, it could count people in the room, chairs in the room, molecules in the room, or something bigger in the universe. Then I have a rule, that's the T, which tells you how things evolve. So you take every point, little x in my space, and I give you some, it moves to some other point. That's T of x. And the rule could have lots of mathematical structure. It could be differentiable, it could be algebraic, it could be geometric, it could be any field that anybody here works in, could be one of what these rules obey. Okay, but for now, right now, I'm not saying the rules obey anything other than just, it's a rule. It's a sum function that tells me where every x goes. And the important point about this rule, though, is it maps x back to x, which means that I can repeat and do x, apply the rule t to it and get tx, apply the rule t to it and get t squared x, and so on. And that's what I get, which is called an orbit. And it's all the points starting with 1. All right, so let's do a very specific example. So here, my space x is going to be the unit interval 0, 1. Okay, so all numbers between 0 and 1 inclusive of the endpoints. My rule is going to say add a fixed amount to each element. So it's x maps to x plus alpha. Now you might say, okay, this is a problem because it doesn't obey my first rule of you take points in the space and you map into the space. So I have to chop off any integer part that I get and do the transformation mod 1. So here's a representation, and I've given you an x here. And now let's look what happens if I map x maps to x plus alpha. So it moves over on the dotted line, which then now looks there. Now what happens if I iterate? I go from x to x plus alpha. Whoops, go back one, yeah. Oops, stay down that one for a minute. Okay, x goes to x plus alpha, and I want to add another alpha. I'm going to fall off the end, right? So I have to instead move back and subtract 1, and now we can go forward, and I really land here and move forward 1 more. So now the iteration moves, instead of going off the end, but it comes back into my space. And now I can repeat. So I move to x plus 2 alpha, and then to x plus 3 alpha, moves the point over, and so on. Here's x plus 4 alpha, and it keeps going. And we could keep going, but I won't write any more. Now, before we move on, I want you to look that I used 2 different colors for the points, x, x plus alpha, x plus 2 alpha. The ones on the left, I've colored them all green, and the ones on the right, I've colored all blue. And it turns out that by chopping the interval into 2 pieces, which I'm going to do on the next slide, I can capture all the information of what's going on here by just looking at the colors that I get, which is a coding. And this is the world of symbolic dynamics. So here's my same interval, but I've now chopped it into 2 pieces. I'm going to color any time I land in the first piece, call that a 0 and color it green. And any time I land in the second piece, call that a 1 and I color it blue. And this is going to generate for me using the same transformation over and over, x, x plus alpha, and so on. Let's iterating it. It's going to generate for x a sequence of 0s and 1s, which are listed at the bottom. So first you go to add x plus alpha, then you go 2 alpha, 3 alpha, 4 alpha, 5 alpha. I think I list up to about 6 or 7 alpha here. Okay, good. So this sequence it goes on infinitely often, right? Because I can keep repeating my transformation over and over. It generates a one-sided sequence of zeros and ones. It turns out that that sequence of zeros and ones reflects everything that was happening in the original dynamical system. So what do I mean by that? Well, if the system I started with, if alpha was very, very simple, next one, then I would get very, very few patterns of zeros and ones. For example, if alpha was, if alpha was 1/4, I would start with some x, and I would add 1/4 to it, and I would add then a half to it, then I would add 3/4 to it, and I would add 1, and I would land back to itself. So whatever pattern I started with, maybe it was 0, 0, 0, 1, 0, 0, 1, 1, I would repeat over and over, 0, 0, 1, 1, 0, 0, 1, 1. It would be periodic. But on the other hand, if I take a very complicated alpha, whoops, I want to go back, go back a little. If I took an alpha that is not rational, an irrational, then I would get a much more complicated sequence of zeros and ones, and the frequency, it turns out, doesn't depend on which point I started with, just on the alpha. Okay, so this is a very particular dynamical system, but more generally, now we can go to the next slide, I want to go back to why the coloring questions that I told you about, Schur's theorem and van der Waerden's theorem and Heinemann's theorem, have to do anything with iterating points in a dynamical system. So I'll give you a general definition, which is to say that a collection of subsets of the integers are said to be partition regular if whenever you color the integers in finitely many pieces, at least one piece in the partition contains the configuration. So we had examples. So rephrasing the theorems that we already saw, we get the first one is Schur's theorem. It says that the triples A, B, C, such that A plus B is equal to C, are partition regular. If we rephrase van der Waerden's theorem, it says that if I take arithmetic progressions, anything that starts with a fixed point and keeps adding the same amount, those are partition regular. And then there was Heinemann's theorem, which was this infinite pattern is partition regular, that you get all the sums that you want from an infinite sequence. Okay, so let's go on to the next. It turns out that you can prove each of these theorems not using combinatorial and counting arguments, they were done originally, but by using a dynamical system, and this time it's a more general one, but you can just think, if you have never seen this before, you can think about the circle, the one that I gave, the x maps to x plus alpha. And in this general setting, though, it turns out that the space x is compact and metric, and the transformation T is a continuous and invertible map. And an amazing insight that Furstenberg had, this was back in the 70s, was that we can translate all of the problems about partition regularity into questions exactly about these kinds of transformations, continuous transformations on a compact metric space. So I will give you one very quick translation which says that how do I go from the combinatorial problem to the dynamical one? Is if you fix an epsilon, you can take your space, x, it's compact and metric, I can chop it up into finitely many pieces, each of which has diameter smaller than epsilon. And then I define a point in there, I look at the point in there and I look what happens to it, and I'm going to define a coloring of the integers depending on the orbit of that point, meaning I set n to live in the jth color, n is colored with the color j, that's the Cj, if and only if the nth iterate of x lands in the jth piece of this chopping up of my space. Okay? And then it turns out that if I start off with a partition regular configuration, it tells me that there exists some p, one piece of my coloring, that contains all of a configuration. You can think of it as it contains A, B, and C, such that A plus B is equal to C. So that tells me that the iterates from this translation, the n in Cj, if and only if t to the nx is in yj, that tells me that t to the nx is in yj for all of the n's in P. Okay? So what does that mean? It actually tells me that when I start iterating t to the nx, I'm always landing in this one piece of P. okay? But the pieces of P were decided to be small enough, so they all land within epsilon of each other, okay? Whatever my metric is on there. And so what this tells me is that the partition regularity property, which is listed here, implies, to the next one, it implies a dynamical regularity property, okay? Because there's a metric on here that says things are close if they have the same entry. So the dynamical regularity, the definition is here. It says a collection P is dynamically regular if for any compact metric space X, for any homeomorphism T from X to X, for any epsilon that you pick, you can find some P in the collection, for example, A plus B equals C, such that the iterates T to the nx all are in some epsilon ball for all of the n's, in our case, A and B and C. Okay? So what this tells me, what we proved, is that the partition regularity implies the dynamical regularity. But that doesn't do much for us, because just if I knew a theorem in combinatorics, I just deduced a theorem in dynamics. And so what's really interesting is the converse, that the dynamical theorems that we could list out prove combinatorial results. So this is, it turns out, and we'll see on the next page, that partition regularity is exactly the same as dynamical regularity, meaning a collection of subsets of the integers is partition regular if and only if they're dynamically regular. So I have given a proof here, but we're going to skip the proof of why dynamical regularity implies partition regularity. And for those who are interested, I can explain it to you afterwards, so we'll skip all of this slide. But the idea, while it's skipping, the idea is that if you start off to find configurations being close, it turns out what you're using is iterates and the compactness of my space. And it really just relies on the compactness and iteration and continuity. Okay, so we'll go to the next slide. That's the proof of the converse. It finishes on this slide. But this is an example of the type of dynamical statement we would then want to prove. So this is a theorem from the 1970s, which Furstenberg and Weiss used to prove van der Waerden's theorem, giving a completely new proof of van der Waerden's theorem using dynamics. And what it says is if you give me any compact metric space X with a homeomorphism T on X, then you give me any K, that's the length of the arithmetic progression that you're looking for, and you take any X in the space and any epsilon, as small as you want, as close as you want. It turns out that you can find some n such that the iterates n, m, that are listed up there in the exponents, t to the mx, t to the n plus mx, and t to the kn plus mx, all are in the same small epsilon ball. And that translates exactly back to van der Waerden's theorem in the integers. Okay. So they also did all of the other ones that I listed, Schur's theorem, Heinemann's theorem, and many others. So what's really going on in these kinds of problems? And one of the questions that we should ask is, did I really need to know that I was only using finitely many colors? Okay, it's clear that if you use infinitely many colors, none of this is going to work because every integer will be colored at a different color. But is finitely many colors important? Is there a different way to rephrase this? So let's look there. I've listed up to 450 to give you an idea. And what if I only colored blue 10%? Okay, hopefully you can see that about 10% of them are now blue. You could ask, can I find patterns just in that 10%? Do I really need this using two colors to color everything, or does 10% suffice? Okay, 10% is an arbitrary but positive amount here. So it turns out that there are much, much stronger theorems behind this. So there was a conjecture, and this is, again, where Erdős comes in. As I said, he liked to ask questions, and Erdős conjectured, jointly with Turan, this is back in the 30s, that if you take any positive percentage, okay, and that's what this set of integers with positive density, any positive percentage of the integers, it already contains arbitrarily long arithmetic progressions. So Erdős did not really make specific what it meant by a positive percentage. He probably meant the natural density, which would be you take your set and you look at how many there are in the first n integers and divide by n. So that's a positive percentage. Okay, I'd get 10% if I do it that way. But you could ask for weaker notions of density, like the upper density, which would be taking the lim sup of that, or the Banach density, where I don't insist that the intervals start from 0. Okay, and you're welcome for the rest of this talk to think about whichever density you like the best. The third one here is the weakest, so giving you the strongest theorems, and every statement I make is true for that one, but you're welcome to think about it as just natural density. Take 10% of the integers. Okay, you'll lose nothing and listen to it that way. Okay, so it turns out that the conjecture of Erdős and Turan was proven by Semeretti in a very famous work from the 1970s, which says that if you take a positive percentage of the integers, you already see arbitrarily long arithmetic progressions in it. Okay? So this proves van der Waerden's theorem, because if you chop up into finitely many pieces using finitely many colors, van der Waerden's theorem said that you have to find one of these, but if you chop up into finitely many pieces, one of them has positive density, because the density better add up to 1. Okay? So it's a stronger theorem, much stronger, and it turns out there have been many, many generalizations of this since then. And let's go back, because these are still, there was a static question this way, but I want to tell you about the dynamical approach, which again was introduced by Furstenberg. Okay, so on this slide, I've again listed about 10%, and here's an arithmetic progression in it, okay? It's, I don't know what the gap is, it looks like 13, okay, is the gap of this one. What happens if I start moving all of the integers and the colors over by 1 to the left? Okay, oops, go back. If you now push forward once and just leave it. Okay, it turns out, well, we're moving everything to the right now, but you see everything sliding over by 1, the colors moving over by 1, and the arithmetic progression moving over by 1? Well, if I do this, an arithmetic progression, when I slide it over by 1, shift it by 1, it doesn't change. It's still an arithmetic progression. That's a dynamical system hidden behind this. Okay, so on the next slide. And what Furstenberg did is he found a way to translate this problem into dynamical systems, but more complicated than the dynamical systems that I was using before, because it turns out now I need behind this a measure space. Okay? So he translated the problem to dynamics and then analyzed the statistical behavior of the resulting dynamical system to find something that was positive. And that implied that he ended up with an arithmetic progression. All right. It's also worked for many other patterns. It turns out that the method that Furstenberg introduced led to polynomial patterns, which means you can start and jump by n squared, for example. There's also ones that are shifted. Okay, they're shifted prime jumps. The primes come into this, meaning you can jump. Well, you can't jump by a prime for certain parity reasons, but you can jump by a prime minus 1 in the arithmetic progressions. Okay, so this is a rephrasing of Semeretti's theorem. It's actually how he proved it. So the original one I wrote up at the top, it says that if you color the integers and you take 10% of them, rather, you just take 10% of them, you'll always find an arithmetic progression. And what the second one does is it takes a compactification version of that. It says you don't need to look at all the integers, but if you take a big enough chunk, the first, I don't know, million, and you color 10% of them blue, you'll find a pattern of length 10 arithmetic progression in there, in the first ones of those. So what Furstenberg did was take that finite version and find out that it actually proves something about measure-preserving systems. Okay, and so what is written here is a statement that follows directly from it, and I leave it for all of the graduate students. I'm going to, after I state this, I'm going to scroll through the proof very quickly, but for graduate students, this is a very nice exercise to prove. You're allowed to assume the top, okay, which means you assume that if I take a big enough subset of the first n, capital N integers, wait, don't scroll through the proof yet, then I can always find an arithmetic progression of length k. And the second one says that the proposition says that if you give me any delta, any length k, any probability space, if you take enough sets, b1 up to bn, where the density of those sets, the size, is at least delta, then you can always find an arithmetic progression along the indices of the sets, where you have intersection that's non-empty. Okay? And the argument is a little bit of a Fatou lemma argument, to give you a hint. Okay, so we'll scroll through that to the next page. So this proposition has, again, no dynamics, but you can turn it into a dynamical question. The next slide. By looking at what this means if I have a transformation on my measure space. Okay? I'm going to be going back to less technical things in 1 minute, but for the moment, what does that mean to be a measurable and measure-preserving transformation? It means that I have some Borel sigma algebra on my space, so you can think of it as just the collection of all the open sets if you want. And I have a transformation such that when I look at something in the sigma algebra, it maps to something in the sigma algebra. And the measure of those two sets is the same. That's the measure preserving. It doesn't change the statistics. Okay, so what the proposition says, that if you have one set, just a single set, with density, and you start iterating it, you look at the set B, TB, T squared B, you keep looking at it, they'll all be sets with the same density, and the proposition tells me that they must have intersection. Okay, the intersection is positive measure. So what we've done here is we've started off with a very, very strong combinatorial statement, Semiretti's theorem, and we have deduced, it turns out, quite strong statement in ergodic theory, a statement about measure-preserving transformations in a measurable system. Okay, and this is the statement that we've deduced, is that you give me any measure-preserving system, you can find an arithmetic progression along which when I iterate a single set of positive measure, you get something of positive measure when I look at all those intersections. Okay, so there's some set B intersect t to the minus a plus db intersect t to the minus ka plus db. And this is exactly Furstenberg's theorem that he proved using ergodic theory. So we started with a combinatorial statement, and we deduced what's known as the Furstenberg multiple recurrence theorem, which was a huge breakthrough in the 70s in ergodic theory. But once again, just like in the case of the compact metric spaces, this is a statement that's much more interesting for the converse. That it turns out that you can prove this and deduce from this the combinatorial statement. And so what I've written up there, you can read or not. It doesn't really matter. But what it basically, the takeaway from it is just to say that when I prove a statement like the multiple recurrence statement in ergodic theory, it implies a statement like Semiretti's theorem in the combinatorial setting. Okay, so this is why the dynamical systems are extremely important. Okay, so I have a proof here of that, which we're going to skip the next two slides for this, but it's basically building on the translation that we had earlier of the principle of going from a combinatorial statement, we can go to the next slide, back to the combinatorial one, from a dynamical statement to the combinatorial one. Okay, so let's, all right. Now, what about statements like Heinemann's theorem? So let me remind you what that is. The statement of van der Waerden, Schur's theorem, those are finite statements. You can find an arithmetic progression of length 10. That's a finite pattern, right? Schur's theorem is a finite pattern. But this theorem of Heinemann says that when you color using finitely many colors, you can find an infinite set, A1, A2, up to whatever, infinite, such that all of the sums, A1, A2, A1 plus A2, A3, A1 plus A3, A2 plus A3, A1 plus, I missed one of them, A2 plus A3, and so on, are all in the same color. What about a density version? Do I really need to color the integers with two colors, or does it suffice to take some percentage of the integers? And it turns out that the answer is no, right? Because think about the odd integers. The odd integers are half of the integers, right? So whatever density you use, it's half. And in the odd integers, when you sum any two odd integers, you leave the odd integers, you get an even. So you can't possibly hope to do this. So of course, this did not deter Erdős from making a conjecture. So Erdős first asked, okay, if I take a positive percent, 10% of the integers, can you always shift them so that I get this kind of infinite pattern? That certainly deals with the odd integers, right? Because when you shift the odd integers, you get the even integers, and you have lots and lots of patterns like this in the even integers, because the sum of any two evens is still even. Well, it turns out that the answer was a resounding no to this one as well. And this is a more complicated example due to Ernst Strauss, who showed that you give me any epsilon, however small you want, I can find a set whose density is as close as you want to 1. It's bigger than or equal to 1 minus epsilon. Okay, so like it could be 99% of the integers, and yet it has no such pattern. Okay, and it's actually a really nice exercise, which I will give you the hint here of what set to use. What you do is you take some very, very fast-growing sequence of primes, P1, P2, P3, and you remove the, you remove the infinite arithmetic progressions of starting at the kth mod k, pk. So you remove these infinite arithmetic progressions. If the sequence of primes is growing really fast, you get something with arbitrary large density, so close as 1 as you want, and it will not have these patterns because you'll run into similar issues like the odd numbers. You'll have parity problems when you add up enough of them. Okay, so this did not deter Erdős at all. He immediately, when this example was presented to him, made a new conjecture. Okay, so this was one of the conjectures he made. He says, if you take a positive percentage of the integers, okay, again, you're welcome to think about it as take 10%. There is an infinite set B. This is a difference between the previous one, but an infinite set B, and there's some shift, because we need to deal with odd numbers. We want it to work in there. There's some shift, oops, go back. There's some shift such that when I add, no, go back, don't go forward. When I add B to itself and I shift, I will end up back in the same set, A. So you take an element B1 in B and another element B2 in B, and B1 plus B2 plus possibly some shift always lands back in A. Okay, so let's think about this for a moment. Is it reasonable? There's no real obvious obstruction, but it turns out that there is this example here which rules this out, that it does not actually contain one of these. This is something which has density close to 1. And so what he probably really meant, because Erdős threw out these conjectures all the time, was to avoid taking the same element B, because that leads to parity problems. If you take B plus B, the same little b in B. And so the real conjecture is he probably made, what he meant was that you can take the set B, add it to itself, so long as you take distinct elements in B. You might have to shift a T, and then you get back into the set. Okay? So that was one of his conjectures, and then he made another conjecture, which I think is on the next. Let me just say some comments about this. First, if you try to do this for coloring, you take finitely many colors, and I color the integers. One of them contains this pattern. Well, we already saw this. That is Schur's theorem, it turns out. Okay, and another comment, next comment, is that you have to allow the translate T because of the odd numbers. You don't want to end up just adding odd numbers and getting out. But it turns out that the translate might only be 0 or 1, it turns out, and that's not so hard to check. Okay. So let's go to another slide. So this is the same conjecture that he made, and there's another conjecture he made at the same time. Let's go to the next, which is a little weaker, because it says that you can find two different sets, B1 and B2, such that when I add B1 from B1 and B2 from B2, you end up back in the same set. The second one implies the first one because I can set the second set to be equal to the translate. I mean, the first one implies the second, sorry. I can set the second set to be the translate of B. And I get the first implies the second. But the second one's a little bit weaker. Okay? All right. It turns out there were a lot of partial results on this. For example, the second one, this is all about the second one. There was no partial results on the first one until very recently. The second one holds, if you start off, you can find an infinite B1 and a finite B2. This is by combinatorial arguments that are really a pigeonhole principle argument. And then there was progress, then there was progress by this 6-authored paper, Donasso, Goldbring, Jin, Leth, Lupini, and Malborg. They showed that if the density is big enough, and they needed the density was bigger than a half, then you get that. Okay, so for example, for the odd integers, which one could do directly, but okay. And then there was a major breakthrough in 2019 by 3 people, Joël Moreira, Florian Richter, and Donald Robertson, in which they proved the second conjecture of Erdős. Okay, so what this says is if you take a set of integers with positive density, 10%, for example, you can always find infinite B1 and B2, so that when you sum one from the first one and another one from the second one, you're back in the set A. So this opens a whole bunch of questions, which I was going to state, but okay, it opens, can you do more? Meaning, why is this just about 2 sets, B1 and B2, but can I do B1 plus B2 plus B3 plus up to BK? And it turned out in joint work, this is my joint work with the 3 others, Joël Moreira, Florian Richter, and Donald Robertson. It turns out that we figured out how to do this for K sets, K copies. The methods are completely different, and I'll say a little bit about the methods in a moment. The second theorem that we proved, also after the first one last year, was that the other conjecture of Erdős also holds. Meaning, if you take a set with positive density, you can always find a single infinite set B, such that when you sum them, B1 plus from B plus B2 from B, then you might have to shift, and you get back in the same set A. So, how do we prove these statements? We are not combinatorists, but we are dynamicists. And so the first thing we want to do is translate all of the proofs into dynamical systems. It turns out that this required a completely new way of translating and changing all of the steps. So what do I mean by this? First of all, even for k equals 2, the one that my collaborators had done previously, this comes up with a new proof. The translation of the combinatorial question into the dynamical question is a new way of doing it, because it turns out that in using the Furstenberg's method, you might end up with nothing in the limit as you start iterating infinitely often. You might have all the quantities going to 0, which for us gives you no information. And what this does is it reduces to a recurrence problem, meaning finding configurations in a dynamical system, like the example that I had given for the theorem of Furstenberg and Weiss. And in this reduction, we need to use very, very strong structure theory from dynamical systems. And these are structure theories about telling us that certain algebraic and geometric structures control the types of configurations that we're using. And so this goes back to work that I had done with my collaborator Bernard Oost back in around 2005 on uncovering what kinds of factors in a dynamical system control the behavior of patterns. and control the behavior of certain averages that arise when looking at these. And it turns out that those same factors of the system are exactly what are used to control this. And this strategy works both for the K sum, B1 plus B2 up to BK, and for the one B plus T, the second one where you find the same set. All right, now, I would say that this is only really the beginning of exploring what types of infinite configurations you can find inside a set with positive density, because this uncovers new methods in order to approach them, and we have lots and lots of questions of what else you can do. So for all of them, you start with a set of positive density, and then the very first one says, okay, if you recall, the second theorem that I had on the previous slide said that there is a single infinite set, so when you sum it to itself, as long as you avoid repeated elements, you end up back in the set with a translate. But our proof does not work for doing that 3 times. Okay, you can take B, and you sum another element from B, and a third element from B, and it turns out our proof doesn't go through. So that's the very first natural question, is can I sum B plus B plus B, or K different times, so long as I take different K tuples, B1 plus B2 plus BK, they're all distinct elements, and land back inside my set. Okay, so that's the first question. There are many, many other variations. Okay, and so this is one of the many. Instead of asking just for that fact that we get B1 plus B2 plus up to BK inside my set, I could ask, can you get B1 union B1 plus B2? So this is asking that B1 be a subset of my set where I'm looking, of my set A that I'm looking for. Okay, so it's a stronger statement. And we have some very partial results for doing this, but the general setting would be to look for K sets, such that when I look at B1, it's in there, B1 plus B2 is in there, and B1 plus B2 up to BK, all of these are inside the set A. And this seems perhaps within reach, perhaps reasonable as a conjecture. And then you can ask, if instead of looking at a set A, which all of this that we've started off with is a set A of positive density, well, what if instead I ask, take a smaller subset of the integers, like the primes. Okay, the primes have 0 density in whatever type of density you're looking at. And so I could ask, do the primes contain patterns? And it turns out in a very big breakthrough from 2010, the primes do contain arithmetic progressions. The version of Semiretti's theorem was proven by Ben Green and Terry Tao in a major breakthrough. Since then, there's been lots of studying, what do the primes contain? Do they contain arithmetic progressions with polynomial skips? And that has been proven. Do they contain all sorts of other patterns like this? And there's a lot of research going on this. And so you could ask, do the primes contain, for the primes, does there exist, just for the very simplest one up at the top, an infinite set, or 2 infinite sets, B1 and B2, such that when I look at B1 plus B2, maybe with a shift, I end up always as a prime? That's an open question, although there's been some partial progress last year by Tao and Ziegler showing that if I always ask for in the same B, and if I always take the first one smaller than the second one, which is a restricted version of this, then you can find such a set. So it's sort of a partial progress towards this question. But there are many others that you could ask. Do all of these patterns contain in the primes? And you can ask about other number theoretic types of subsets of the integers. Do they also contain these kinds of patterns? Okay? So with all of those open questions left for you to solve, I will say thank you.
Thank you, Bryna, for your very interesting talk. Are there any questions, preguntas, English o español? Aquí.
And there was-
Dila fuerte.
So logarithmic density is easier because you get more. So that is a really good question because for many of them, the first one to test is logarithmic density. And so we do that in all of them. And we have some patterns that we know occur in logarithmic density large sets, but not, usually once we get one, we get the other. But it's a really good question because it's an easier test case.
Aquí había una. El micrófono está ahí.
A simple question. In the Science Museum in Mexico City, there's a very nice thing. In the computer, you type the year you are born, your month, and then it tells you exactly where, in the expansion of the number of pi, where exactly you find that. I presume, is that a special case of...
Yes, so the expansions of numbers, when I did the iteration of the irrational rotation, we were looking at the binary expansion of alpha, in fact. And so symbolic dynamics captures all of these and is a great way to look for patterns in things. Unfortunately, most of our results say that most numbers have patterns, and so we'll never be able to say specific things about a particular integer, or a real number rather. But one of the difficulties that we use here, have to overcome here, is we need several statements that are true for all points in our space, which is not a very ergodic statement. It's not a measurable statement, so we actually have to use a combination of measurable and topological methods, in particular very strong symbolic methods, to get statements for all points in the space. And so perhaps there's some use of this in other contexts, but it's all preliminary.
Aquí hay otra pregunta. Sí. Si tienen dudas, por favor, acérquense al micrófono.
This works for telescopic summary problems, ones that are using the Olympians,
Can you say again?
the Math Olympians. Can we use this in the combinatory problems that contain telescopic summary of the Math Olympians?
So I have seen Math Olympiad questions that are very combinatorial like this. So for example, here's one which you might be able to prove. Let's say you color the first 100 integers with red or blue. Okay? Find me a rectangle, list them 1 through 10, 11 through 20, and so on, like this. Find me a rectangle such that the four corners are all either red or blue. Some rectangle. You have to prove that there always is such a rectangle. In fact, I think you only need 27 numbers to do this. So you can list out the first 27. As long as you list them in a grid some way, there's always, and color them red or blue, there'll be a rectangle that always has the same color for all four corners. Just the corners, not the whole rectangle.
Thank you.
¿Alguna otra pregunta? ¿Te puedes ir al micrófono?
Thank you. Two questions. In the next to last statement that you have, the conjecture, what will happen if you change to all combinations of finite sums? Would that be easier to prove or harder to prove?
So you mean B1?
B1 union B1 plus B3 union.
Yeah. In fact, that's a really good question, and it would be false.
Okay.
And we have a counterexample to that in a paper that I hope to put on the archive soon. But it's a really good question because originally that was what we had put down as our conjecture until we came up with a counterexample.
Because that sounds more like the IP sequence that you have talked about before.
It does, yes.
And the other question is, in the first example that you mentioned, where you have x plus alpha, x plus 2 alpha, etc., you said that the sequence that you get when you color by zeros and ones does not depend on x? Is that what you said, or I misunderstood you?
Yes, that is correct. It depends. What I said is the frequency of the zeros and ones.
Oh, the frequency. Okay,
Yeah.
because if you start with the left.
Yes.
Okay.
Right. So the frequency of zeros and ones is independent of x, and
Okay.
it captures the alpha.
But the sequence itself is not. It does
No,
depend
the
on X,
sequence
okay.
itself changes because if you move x over, you might start with blue versus green,
Right.
etc.
And could you recover the X or the alpha just by looking at the sequence?
You can recover the alpha by looking at the sequence up to pretty much you can recover the alpha, but the x, no.
Okay.
You don't know where it started.
Thank you.
Yeah.
Richie.
Hi. This is just a comment. Thank you for your talk. It was great. And about Erdos, at the beginning, he wrote lots of papers, lots of co-authors, but he only wrote one review in mathematical reviews. And in that paper, there's another open problem. That's it.
Yes, I know that. I almost put that on my slide, and I thought not everyone knows what mathematical reviews would be. Yeah, it's a good point. Erdos didn't write much by himself, so he basically would give his problems and his proofs to other people to write because it wasn't his thing to write.
Les comento que a las 12 del día Bryna dará una presentación de cómo trabaja la Sociedad Matemática Americana junto con Fabián Durán, que presentará acerca de la Sociedad Matemática Francesa en el auditorio del Centro de Emprendimiento que está al lado del estacionamiento. So now I would, from the local organizing committee and the scientific committee, I would like to thank Bryna for coming. Thanks.